Hi guys, and welcome back to my channel. In this video we're going to be discussing ionic structures and the properties that come because of these specific structures. So to watch this video you really should have seen my unit cell video or know about the different types of unit cells and the holes that are within the unit cells. Because basically in this video we're just applying those exact same concepts and talking about a few specific structures that are really common, in which basically one ion is going to fill. So say for example NaCl, we'll talk about the structure in the video, but one of these ions is going to form the actual unit cell, and the other ion is going to go into the holes within the unit cell. So we're just going to talk about specific structures like NaCl, for example, in this video. So you really should have had that understanding of the types of unit cells and the holes within the unit cells. So let's just get right into it. Alright, so as I just was mentioning, we're going to first discuss the NaCl structure. So to just go over this quickly, you can see in this image here, this is the NaCl structure. The blue ions represent the chlorides, the red represents the sodium, right? And essentially what you can see is there's an FCC lattice of chloride anions, and the sodium cations are basically filling the octahedral holes. And you should know what FCC lattices are and octahedral holes are from the unit cells, the previous unit cells video. So if you don't understand that terminology, again, go watch that video. But one thing that's important to sort of confirm is that we know that the Na plus and Cl's, right? Sorry for that switch in color. We know that the Na and Cl's, Na plus, the ratio of Na to Cl is a 1-to-1 ratio, right? That's just our stoichiometric ratio. We have one sodium cation for one chloride anion. So we want to make sure this unit cell contains that same information. It agrees with our, obvious knowledge. So let's look at our unit cell and figure out how many of each ion are in the unit cell. So let's first look at FCC lattices, right? Remember we have 8 corner atoms, and we have the 6 on the faces, and each face is shared by 2 unit cells. So this gives us 8 times 1/8 plus 6 times 1/2, which gives us 4 ions total. So we have 4 chloride anions in this unit cell. Now let's look at sodium, right? And if everything goes well, we should get 4 sodium ions as well. So we keep that 1-to-1 ratio. Let's just make sure. So octahedral holes, right? There's one in the center, which isn't shared by any unit cell. So we just have one. But then we have, the 12 on the edges. And remember, edges are shared by 4 unit cells. So we have 12 times 1/4. And that gives us 4 ions if we sum that together. So and everything is good. This agrees with our normal intuition. We have 4 sodium ions for every 4 chloride ions, which makes sense. We should have this answer, right? And the next thing I want to talk about is the coordination number. And this is just an important concept that will keep coming up in this video, and is just a good piece of terminology to know. So coordination number just means how many nearest neighbors are around a certain ion. So 6-6 coordination with the NaCl lattice, what does that mean? That means that with both the chloride and the sodium, we have 6 nearest neighbors. So let me look at a specific sodium ion, because every sodium ion it's going to be the same, because it's a unit cell, right? You just move it around and essentially it's the same, it's symmetric. Like no sodium ion is more special than another sodium ion, right? So every sodium ion will have the same coordination number, and same with the chlorides. So if I pick one that's easiest for me to look at, that's fine, right? So what I'm going to do is I'm going to pick the center sodium ion. So if I look at the nearest neighbors, I see that I have a chloride to the top, a chloride to the right, chloride to the bottom, chloride to the left, and I have chlorides in and out of the page. So you can see that I have 6 nearest neighbors, 6 chlorides that are closest to the sodium ion. And that's where I get my 6 coordination, right? And you can sort of see that it also looks like an octahedral, it looks octahedral, right? I have this square planar sort of base, and with my 2 axial bonds, it looks like an octahedral sort of coordination, and that is exactly correct, right? And that's sort of why we have this notion of octahedral holes, right? It's filling it in such a way that we're creating this like octahedral coordination environment. So that's another important thing to notice. And so we've confirmed for sodium. Now let's look at a chloride, right? Say I pick this chloride here right on the face. It doesn't matter which chloride I pick. Everything is the same. So you can see I have 4 right here. I have 4 nearest neighbors of the sodiums that are, in and out of the page, up and down. And I also have this one to the left, right? And if I drew another unit cell, if I copied and pasted this unit cell and sort of moved it to the right, you would see that I have a nearest neighbor also to the right. So essentially for the chlorides, I also have this sort of octahedral environment and a 6 coordination. Okay, so that's what coordination number is. It just tells me, how many nearest neighbors does my ion have? And that's an important concept that will come up with different structures in this video. All right, so the next structure I want to discuss is the cesium chloride structure, right? And in this structure, you see that we have a primitive cubic lattice of chloride minus anions. So we have these anions that are forming a primitive cubic lattice. And remember, in a primitive cubic lattice, we have cubic holes, right? So these cesiums, the cesium plus fills the cubic holes, right? Which is right in the center of the cube. And so you might be wondering, why does NaCl and cesium chloride have, different structures, right? Both are in a 1-to-1 ratio. So what influences one to have a different structure than the other? And remember, when we talked about holes, we talked about the sizes of cations that fit the holes. So remember, we had in the previous slide with NaCl, we had sodium fitting octahedral holes. Octahedral holes are much smaller than cubic holes. And that makes sense, right? The cesium is a much bigger cation than sodium because it's farther down on the periodic table, right? So what that means is that it's going to need a bigger hole to fill. So that's why instead of filling these octahedral holes, which are too small, it's going to fill cubic holes, and this chloride is going to be forced into a primitive cubic lattice. So remember, when we're thinking about like predicting structures, we're thinking about what is the size of the cation that's going to be filling the holes, or the relative sizes, right? Okay, so that is why basically in the cesium chloride structure, we fill the cubic holes and not the octahedral holes. And next, again, we want to talk about coordination. So this is kind of, a little bit obvious to see. But if we look at the coordination of a cesium plus ion right here, you see that there's 8 of these chlorides that are its nearest neighbors, right? We see these 8 chlorides that are its nearest neighbors. And if I looked at each of these chlorides, it's really difficult to see in this picture. But if I looked at each of these chlorides and I stacked a bunch of unit cells on top of each other and to the sides, such that it sort of represented more unit cells and a bigger piece of the crystal, I would see that these chlorides also had an 8 coordination number. And these 8 would come from different cesiums that pop up all over the place. So each chloride is actually, its nearest neighbors. There are 8 nearest neighbors, and each of them is a cesium, a cation. Another thing that's kind of interesting is that, for both the NaCl structure and the cesium chloride structure, switching the sodiums and the chlorides, I know how I said the anion makes the unit cell and the cation will fill the octahedral holes, but technically they're exactly the same thing, right? I could, for example, if I put chloride in the middle of this, and I put, so if I switch these two, right? If say my cesium was, I'll X this out, so my chloride was blue, and my cesium was red, this changes nothing, actually. This is the exact same unit cell, essentially. Because if I stacked a bunch of these unit cells, it would just look like a slight shift in perspective. But the entire crystal would be actually exactly the same, which is kind of interesting, right? And it's really hard for me to show on just looking at one unit cell. So I really, recommend that, you go and try and visualize this and create this structure and copy and paste it multiple times and see it for yourself, right? You'll see that essentially the chlorides and cesiums are interchangeable, and this is the same exact thing with the sodium and chlorides in the previous slide in the NaCl structure. So that's why we have this 8-8 coordination. We have 8 coordination for the cesium, and obviously because I just said, cesium and chlorides are interchangeable, we'll have 8 coordination for the chlorides as well. Okay, so now I want to talk about the fluorite structure, and this is commonly CaF2, right? That's the sort of canonical example that this structure that takes this structure. And then with the fluorites, we also have the anti-fluorite structure, which is essentially the same, except the anion and cation switch places. So note here, right, we don't have a 1-to-1 ratio of cation to anion. So where the anion is relative, if the cation is filling the holes, whereas the anion is creating the structure, that's going to matter, right? Because if I flipped it, then I should have a different stoichiometric ratio. My ratio would have swapped. So if that makes any sense, let me just explain it really quickly. So for example, if the cation filled the hole and the anion was the structure, and the anion, like for example fluorite, we had 2 anions per cation, right? If I flipped it, right, if I flipped the cations and anions, now suddenly I would have 1 anion per 2 cations, and that would be a whole different structure. So unlike my cesium chloride and my NaCl, it actually matters in this case. So I just want to stress that because I just said, in the previous slide that you can switch the two and it doesn't really matter. In these cases where the stoichiometric ratio is different, right, is off, it is going to matter because it'll flip your stoichiometric ratio if you flip the positions of the anions and cations. Okay, so in a fluorite structure, we have a face-centered cubic lattice of Ca2+ cations. So we have FCC lattice of the cations, which is interesting, right? This normally doesn't happen. And we have the fluorides filling these tetrahedral holes. Why is the cations filling, creating the unit cell? Generally, remember, the bigger ion is going to create the unit cells, the smaller ions are going to fill the holes. And in this case, calcium is a bigger ion than fluoride because fluoride is such a small ion, right? It's all the way up in the periodic table, it's all the way to the right. So it's got a high nuclear charge, so it's going to be pulled really close to the nucleus. It's a small atomic size, small ionic radius. Right, so fluorides are small, that's why they're filling the holes. Generally, anions are bigger, and why is that? That's because you've added an electron. You've added more electrons than the nucleus has in positive charges, so you have this extra electron-electron repulsion making the anion bigger. Whereas in the cation, you've removed electrons, but you have the same nuclear charge, which makes the radius smaller. Right, so generally you have anions being bigger, but in this case, because it's fluoride specifically, it's such a small anion, we have the anion filling the holes. Okay, so we have this FCC lattice. We know what FCC lattices are, right? We've got the stuff on the faces and the stuff on the corners, and then we've got these F minuses in the tetrahedral holes, right? Okay, so if we do the counting, remember that we have 4 calcium cations in the on the lattice, right? We calculated it in the NaCl structure how many atoms are in an FCC lattice, and then for the fluorides, right? We have a fluoride in each of these tetrahedral holes, and remember, tetrahedral holes are within the unit cell; they're not shared, right? They're not on a face, they're not on a edge or something like that. So we just have 8 fluorides, which agrees exactly with our ratio, right? 1 calcium per 2 fluorides, 1 Ca2+ per 2 fluorides. That's our stoichiometric ratio, which is good. Now let's look at our coordination, right? So let's look at a calcium. You can see that we have 8 coordination for a calcium. It's a little bit difficult actually to see, or it's not too difficult, but let me look at this side calcium actually, make it a little easier. You can see that we have these 4 bonds to these fluorides drawn in, right? So we have 4 coordination there. Now if I copied and pasted this unit cell and moved it to the right, you would realize that I also have 4 on this side. So what does that mean? That means we have 8 total. And remember, with all of these unit cells, we're allowed to just look at pick one calcium or pick one fluoride, because no calcium is going to be more special than another. No calcium is going to have a different coordination number than another. So I can pick whatever is easiest for me to see. So that's why we have 8 coordination for these calciums. For the fluorides, it's a little bit easier to see. I can just pick one of these guys, right? One of the fluorides. You can see that it's in a tetrahedral arrangement. I have 2 calciums here, 2 calciums there. So I have 4 total coordination number, right? And that's sort of given by filling tetrahedral holes. Remember, a tetrahedron it's a 4 coordinated structure, right? That's a tetrahedral structure. So we have 8 for coordination. We have a coordination number of 8 for the calciums, coordination number of 4 for the fluorides. Okay, and just to, mention that what fluoride structure is the fluoride structure is what is drawn here. We have the anions filling the tetrahedral holes. And what does that mean? That means the anions are smaller than the cations. So our fluoride is smaller than the calcium. Whereas we can also have anti-fluoride structures. And that's basically the same idea, except the cations fill the tetrahedral holes. So that means the cations in this case are going to be smaller than the anions. And an example of this is lithium 2 Li2O, right? We have oxygen basically filling the FCC lattice sites. So we have 4 oxygens in the unit cell. And then we have these lithiums filling the tetrahedral holes. So we have double the number of lithiums as oxygens. All right, so that's the fluoride structure. Now let's talk about the zinc sulfide structure, and this is really similar to the fluoride structure, except you can see that only half the tetrahedral holes are filled. So really similar to fluoride, we have the same idea going on, right? We have an FCC lattice, and then we have tetrahedral hole filling, right? But you notice that zinc sulfide doesn't have, it's in a 1-to-1 ratio, right? So zinc sulfide in a 1-to-1 ratio. So this immediately sort of tells us that only half of these tetrahedral holes can be filled. Because if all of them were filled, we would have more, more of whatever is filling the tetrahedral holes, which is the zinc. We would have more of the zinc than the sulfur. So just to confirm, remember that we have 4 of all the FCC. If I counted all the atoms in the FCC lattice, we have 4 of those. And the lattice is the sulfur. So we have 4 sulfur anions. And remember that we have 4 of these zincs filling the tetrahedral holes. And each zinc is not shared between any unit cells. So we just have 4 zincs. Right, and this agrees with our stoichiometric ratio. We have 4 zincs to 4 sulfurs, which is a 1-to-1 ratio, which is exactly what we expect. So essentially, this zinc sulfide is just FCC lattice of our sulfur anions, with the zinc filling the tetrahedral holes. Exactly what I said previously. But remember, you might think a good question to ask is, what makes this different than NaCl? Right? Why don't we just have, an FCC lattice with the zinc filling the octahedral holes like we had with an NaCl structure? The reason is that octahedral holes are not filled because the zinc cations are too small. Zinc cations are too small. So remember, tetrahedral holes are the smallest holes. Then we have octahedral, and then we have our cubics. So because the zinc cations are actually, smaller relative to the lattice compared to the sodium cations, we have the zinc cations filling the tetrahedral holes rather than the octahedral holes. And when I mean smaller relative to the lattice, I mean the ratio of the size between the cation radius and the anion radius. So remember in the previous video we talked about how this ratio is going to cause different holes to be filled. The zinc cations are too small and thus fill the smaller holes, which are the tetrahedral holes. Now let's look at the coordination number. So again, you don't really have to memorize these coordination numbers. I just want you to be able to be able to look at a structure and sort of figure out the coordination number from that, right? So let's look at, let's look at a zinc, for example, first. We have a zinc in the tetrahedral hole. Again, remember tetrahedral holes are going to have, or things filling tetrahedral holes will have 4 coordination because we have, basically a tetrahedron that's being formed to these sulfur anions. So we have a 4 coordinate, which gives us, for the zinc, 4 coordination number. But also for the sulfur, we also have a 4 coordination number. And this is different than our previous slide, remember, because in the previous slide we had 8 coordination number. It's different because we only have half the tetrahedral holes being filled. So for example, you can see this bottom sulfur here. We have a 2 coordination to zinc up above. But if I copied and pasted this unit cell down below, I would have 2 down below, right? So for the sulfur, we also have 4 coordination. So for coordination number, it's not really important to memorize these, but it is important to be able to look at a structure and be able to figure it out. Essentially, all you're doing is looking at how many nearest neighbors are there, and they're going to be the nearest neighbors of other ions, right? They're going to be the nearest neighbors are going to be the other ion. So for example, if I'm looking at a sulfur anion, the nearest neighbor is going to be, that I'm looking for, is going to be a zinc cation, right? So that's how I find the coordination number. Okay, and now finally we're going to talk about this titanium oxide structure or rutile structure, right? And this is our last structure that we're going to talk about, and this is a little weird compared to the others because it's actually not a cubic structure. It's a sort of tetragonal lattice, which basically means some sort of like rectangular prism. And because of this, the holes in the lattice are different than the holes in a cubic lattice. So it's not super important to, memorize the structure, but I just want you to be aware of this because it is actually a relatively common structure that you might see. So in this structure, we have this body-centered tetragonal lattice of titanium 4+ cations. So what does that mean? Body-centered tetragonal lattice, you can sort of kind of guess, right? Just like from body-centered cubic, we have the 8 on the vertices, and we have the 1 in the center. That's the body-centered, right? Just like body-centered cubic. So let's count the number of atoms, right, or ions. We have 8 on the vertices that are shared by 8 unit cells, so it's 1/8. And then we have the 1 in the center, so that gives us 2 total, right? 2 total Ti4+ ions, right? And we also know that these O2 minuses are in what we call trigonal holes. And that's kind of, trigonal holes sort of sounds like, it's similar to tetrahedral holes, but remember how in tetrahedral holes we had 4 coordination? In trigonal holes, we're going to have 3 coordination. And you might want to think about it like you think about trigonal planar, for example, something like that. So let's look at this oxygen. It's in this what we call trigonal hole, and we can see this sort of trigonal planar coordination happening here, right? Where it's bonding to 3 different titaniums. So now let's count the number of oxygens in the structure. We have these 2 oxygens that are within the unit cell, which means that they're owned solely by this 1 unit cell. But we have 4 of these oxygens that are on the faces of the unit cell, right? 4, and when it's on the face, they're equal to half, right? Only half of it is owned by this unit cell. If we do the math, we get 4 total oxygen, 2 minuses, right? And this ratio again agrees with our stoichiometric ratio, we have 2 Ti4 plus for 4 oxygens, which means 1 titanium per 2 oxygens, which is exactly what our stoichiometric ratio suggests, right? So that's good. Now we look at coordination number again, right? So for oxygen, it's filling trigonal holes. So if it's filling trigonal holes, we have a 3 coordination number. So if I look at this oxygen, just to make it more clear, we have these 3 bonds to the titanium ions, right? So we have these 3 bonds, that's our 3 coordination number. And for titanium, I can look at the center one really easily, and we see that I have 6 bonds to different oxygens, right? We have 1 here, 1 here, 1 there, 1 there, 1 there, and 1 there. It's right in the center, so it's really clear to see, right? So we have these 6 nearest neighbors of oxygens, right? So we have a 6 coordination for the titanium. In other words, this is a 6-3 coordination structure, right? 6 for the titaniums, 3 for the oxygens. Now, in the next slides, I want to discuss defects in these lattices and sort of what that means and why they're important, right? So first we're going to talk about intrinsic defects, right? And what are intrinsic defects? That means they occur in pure lattices. So this is important. This is what makes an intrinsic defect versus an extrinsic defect, which we'll talk about in the next slide. Okay, so there's 2 main types of defects. One is the Schottky defect, and the other is the Frankel defect. First, we're going to talk about the Schottky defect. Essentially, what Schottky defect means is that we have these vacant lattice sites, and essentially these ions, the ions in the lattice sites that are sort of removed, are removed in a way such that the compound remains neutral, which makes sense, right? Essentially, in total, we have to have a neutral compound, so the removal of these ions are in a way such that we have a neutral compound after the removal, right? And this generally occurs in highly ionic compounds with similar size ions and with high coordination numbers of 6 or 8. So for example, NaCl. So let's just give, an example of this removal. If we had NaCl and we removed an Na plus ion, that means we would also have to remove a chloride ion to keep the compound neutral. And that would be a defect. So if we look at sort of this picture, we can see that we have 1 positive ion and 1 negative ion, anion, missing, right? So we're basically removing them in a way that keeps the compound net neutral. But for example, say we had like CaF2 and we had a Schottky defect. What would this mean? That say we removed 1 Ca2 plus, 2 fluorides would have to be removed to keep the compound net neutral, right? So this is, that's why we have, so we got to worry about the stoichiometric ratio when we're looking at how many ions are removed due to this defect. The next defect I want to talk about is Frankel defect. So essentially, Schottky defect is things being removed. Frankel defect is stuff being moved around. Okay, so what the Frankel defect is an ion is displaced into vacant interstitial sites, and a simpler way of phrasing that, or one example, is an ion in an octahedral hole is moving to a tetrahedral hole. So basically these ions are moving around rather than being removed from the compound altogether. The picture, you can see this a little more clearly. We have this positive ion that used to be in this site, and it sort of just moved up there, right? You can see it's placed in a different position now. Essentially, we're just moving ions around, so the compound again is remaining net neutral. But there's this sort of like vacant lattice site, kind of, right? Because of the movement of this ion. And this generally occurs when we have significant difference in anion-cation size and with small coordination numbers of like 4 or 6. So why is it, occurring when there's significant differences in size between anion and cation? If the ion sizes are very different, right, there's going to be extra space in the holes of the unit cell, So, and these defects that are formed are going to be caused by ions moving between these holes, because there's extra space in these holes of the unit cell if the sizes are very different. So if sizes are very different, extra space in holes, so you're going to have ions being able to move between holes, right? And that's when you're going to have the Frankel defects. Otherwise, you have the Schottky defects, which is when the size of the anion and cations are pretty similar. Now I want to talk about extrinsic defects, right? And this is, opposite of intrinsic defects, is these are caused by when you add something into lattice, right? So the intrinsic defects were in pure lattices. Now we have extrinsic defects when I sort of add stuff and now there's a defect. So let's give a clear example. For example, if I doped zirconium oxide with calcium 2+, so zirconium oxide, right, we have Zr4+ and O2- ions in my cell. If I doped this with calcium 2+, this calcium 2+ is going to replace the zirconium 4+. But to keep it neutral, right, we need to remove some oxygens, because it's going to be negative if I replace a zirconium 4+ with a less highly charged cation, right? So basically, we're going to have O2- vacancies, these oxide ion vacancies that are necessary to maintain this zero net charge, and that's caused by this extrinsic defect of me doping, zirconium 4+ with calcium 2+. Another example of an extrinsic defect is an F center, and these are really actually quite interesting. I'm not going to go into them too much in this video, but what an F center is electrons that are trapped in a lattice. So that's what this picture is showing. This is an F center. Okay, so how is an F center formed? In this case, we have sodium and chloride, right? And that's the case I'm going to talk about. Say we had sodium gas that's sent through a sodium chloride lattice, right? What's going to happen is the sodium gas is going to oxidize, because it's so, sodium is so easily oxidized. So this sodium gas is going to oxidize and form Na+, and this Na+ is going to go and join the lattice, right? But where does that lost electron go? Instead of the chloride, right, remember how when we add another NaCl, usually there's an Na and a Cl pair in a 1-to-1 ratio. But if I just put Na gas through this lattice, it oxidizes, loses an electron. This electron is sort of going to fill the place of the chloride. So this lost electron fills the lattice where the chloride would have been. So you can see here, this is where the chloride would have been if we continue this, two-dimensional lattice. But instead, there's this just lone electron that's sort of hanging out. And these F centers are paramagnetic. And what is paramagnetic? That just means that there's a presence of an unpaired electron, right, which is obviously this electron right here, because it's not sort of paired with another electron. It's just floating around by itself. And because of this, it has interesting magnetic properties that come from this unpaired electron that were not there because of just the pure lattice. Because say if we had a chloride instead, if this was a chloride, right, we would have all paired electrons. There would be 8 paired electrons in a chloride minus ion, right? But in this case, we just have a pure electron. So we have an unpaired electron. So this gives properties that aren't going to be there in a pure NaCl lattice, and that's why they're so interesting to study. And finally, let's talk about alloys. So you probably heard about this in, AP chemistry. We have substitution alloys and interstitial alloys. Substitution alloys just means that atoms in a metal lattice are substituted with other metal atoms. For example, we have AuCu3, and in this alloy, basically we have a gold FCC lattice. So we have an FCC lattice, but the facial sites, remember how in FCC we have the corners, the vertices, and the faces. filled with atoms, so the facial sites are substituted with copper. So essentially, we're just taking this normal metal lattice and substituting other metal atoms in for the atoms in this pure metal lattice. Whereas in interstitial, we have a slightly different situation going on. Interstitial, we have a metal filling the holes in the lattice of other metals, right? And if a metal is filling the holes, that means it must be smaller than the original, than the metal that's filling the entire lattice. So this happens with metals with very different ionic radii, right? One needs to be much smaller than the other to fit into the holes. All right, so now for the last few slides, I want to switch gears and talk more about energetics. So we're going to talk about energetics. And we've sort of mentioned these, energetics before, especially the Born-Land equation, so I just want to give a quick review. The Born-Land equation approximates the potential energy of ionic lattices, and that's sort of given by this equation here. So you can kind of see that we have some sort of constant, right? We have this potential energy equals some constant, we'll call this C, times ZaZb. ZaZb tells us how highly charged, right? Za is the sort of, if I had calcium 2 plus, the Z would be plus 2, right? If I had, S2 minus, the Z would be minus 2. So it tells us the charge, right? So I have a constant times the product of these charges divided by the distance times some A. And this A is basically a constant that is determined by the type of lattice you have. So I can basically combine this A and the C, so I'm just going to call this one big C. And of course, if you actually wanted to calculate the potential energies using this equation, you would need to plug in these numbers. But right now, I just want to see the main relationships. We have, the potential energy being inversely related to distance and proportional to the Coulombic, the magnitude of the charges. This is exactly basically a Coulomb's law type of expression. So we have so this approximation is basically assuming purely ionic interactions, right? It looks exactly like Coulomb's law. So that means this equation means that there's no sort of repulsions when ions get close to each other from overlapping electron clouds. So this is not a perfect, equation, right? There are better equations to model it, but, generally, if we're just trying to approximate stuff, we can use this equation such that U is equal to, this Coulomb's law type expression. And what's important, what I really want to stress, is that our potential energy is proportional to 1 over the distance between the ions, right, in a lattice. So, for example, Na and Cl, if I had an NaCl lattice, the distance between the sodium and chloride is going to be what U is proportional to. And if I say, for example, I draw a sodium chloride, we have sodium here and chloride here. The distance between these ions are the distances between the centers, right? The distances between the centers, which is equal to the radius of the sum of the radii of each atom, right? So U is proportional to the 1 over distance, which is 1 over the radius of the cation plus the radius of the anion. And that's my notation here. I've written R plus and R minus. That's the radius of cation and the radius of the anion. So in our next slides are going to be using this potential energy approximation to sort of approximate or use this approximation to reason properties of ionic salts. So for example, why does some decomposition happen whereas other decompositions don't, and stuff like that, right? Essentially, we're gonna look at the potential energies of products and reactants, and we can think of potential energies kind of like enthalpies. So it'll tell us how much energy is gained or lost in a certain process. So anyway, let's just move to the next slide. The first thing I want to discuss is thermal stability of ionic solids. So an example of this, and the example we're going to look at, is a carbonate salt. Carbonates decomposing. So we have a metal carbonate, like MCO3, going to MO and CO2. So, you know, we have like, for example, calcium carbonate or barium carbonate or something like that decomposing to calcium oxide and CO2, barium oxide and CO2, right? These are just some examples, but what is important is that, yeah, so we're going to look at this, and if we want to look at the spontaneity or how, you know, how spontaneous this reaction would be, we generally look at delta S and delta G and delta H, right? If we want to look at spontaneity, we look at delta G, which is determined by enthalpy and entropy. If we look at the entropy change, we have CO2 being produced. So we obviously have a delta S greater than 0 because we have a gas being produced from a solid, right? But also, we have delta H greater than 0. Why do we have delta H greater than 0? Because we're breaking bonds, right? If we're going from metal carbonate to metal oxide and CO2, we have to break those bonds of the carbonate to release the CO2, right? So we have a net breaking of bonds, so we have a delta H greater than 0. But the lower the delta H, the more spontaneous the decomposition. Because remember, delta G is equal to delta H minus T delta S. So if we have delta S greater than 0, that's good. That makes delta G negative. But if we have delta H, you know, the smaller delta H is, and the less positive delta H is, the more negative we'll have delta G, which means the more spontaneous the reaction will be. So we want to look at delta H changes. And what we can do is we can sort of think of delta H as similar to delta U. Okay, so delta H sort of tells us how much energy is taken to release, you know, to break these bonds. Delta U tells us the net energy difference between the two states, the final and the product and the reactant. So we can sort of use delta U and look at our delta U understanding, right? Look at our change in potential energy and sort of reason that that'll be the same as the change in enthalpy. Because, for example, we're looking at the change in delta U between our carbonate and our oxide. So if our metal oxide is lower in potential energy, or quote unquote more stable, then that's probably going to mean a lower delta H. Whereas if our metal carbonate is, you know, more stable than our metal oxide, that's going to mean sort of a higher delta H in terms of this forward reaction. Okay, so let's just go and calculate our percent change in delta U, or in potential energy. So when I'm looking at percent change in U, I want to look at the change in potential energy divided by the initial potential energy, right? And remember, potential energies are proportional to 1 over distance. So I can write change in potential energy as sort of like, if I'm just looking at ratios, the change in potential energy is going to be proportional to 1 over the distance final minus 1 over distance initial. And we're dividing by 1 over distance initial, because that's the initial potential energy, or what it's proportional to. And if you do some math, you know, and sort of rearrange the terms, you can get this to say that we have distance initial minus distance final over distance final, right? If we just like do some multiplication on the numerator and denominator, we'll end up with this expression here, which looks a little bit nicer. And we know that what is the distance initial and what is the distance final, right? If we treat the metal and the carbonate as just two ions, which we should, that's a good approximation, our distance initial is just the radius of the metal plus the radius of the carbonate ion. And our final distance is the radius of the metal plus the radius of the oxygen anion, right? So if I substitute these values into this expression, what do I get? I get that the percent change in U is equal to the radius of the carbonate minus the radius of the oxygen divided by the radius of the metal plus radius of the oxygen. Okay, so essentially the larger change in the delta U, right, the larger percent change, we know that this percent change is going to be negative, right? It is negative. But the larger percent change in delta U implies a smaller delta H decomposition, right? Which means that it's going to decompose more readily. So what's important with this slide is that you can basically approximate how how stable these compounds are going to be by just looking at the percent change in the potential energy. And if there's a huge change in potential energy, if it lowers in potential energy a ton, what does that tell us? That tells us it's probably a favorable process, and our delta H is going to be, it's still going to be positive because we're breaking bonds, but it's going to be small and positive. Whereas if there's, just a tiny decrease in potential energy, that tells us that, okay, it's not super favorable. So our delta H will be, positive, but much more positive. It's not going to be as favorable. So that's what our percent change in in potential energy is going to tell us. And, the next property I want to talk about is solubility of ionic salts. So in terms of solubility, we want to think about the lattice energy and the hydration energy, right? What is solubility? Like, if I put something in an aqueous solution, there's two steps, right? I first got to break the ions apart, and then I got to form interactions with the water, right? If I have like NaCl, I first got to break it into Na plus and Cl minus, and then, there's this process is going to take energy for me to break these ions apart. But what releases energy is the chloride interacting with the water molecules, interacting with the water molecules like this, forming a little shell, which is called hydration, and the sodium's interacting with the oxygens, the water molecules, or the oxygens in the water molecules, right? So we first have this, input of energy, which comes from the lattice energy, and then we have this release of energy, which comes from the hydration. So let's look at, the delta. What are these delta H's proportional to? We have lattice energy is going to be proportional to remember, it's 1 over distance. If I look at a certain, so here we're using delta H sort of interchangeably with potential energy, which is not entirely correct, but it's a good enough approximation for our use in this system. We're going to talk more about thermodynamics in future videos, but in this case, just know that we can sort of treat enthalpy as the same thing as energy. So in your AP Chem, you might have just thought about these interchangeably, right? Enthalpy is telling me how much energy I'm sort of gaining or losing in a certain reaction. That's what potential energy is doing. How much energy am I losing by going from a product to a reactant? So it's really similar. And that's why we're using these same sort of concepts for, like my initial Born-Land equation was talking about potential energy, but I can use these relationships to talk about enthalpy as well. So our lattice energy is going to be proportional to the distance between the ions, right? The closer the ions, the harder it is going to be to rip them apart. So I have 1 over the distance between the ions, which is 1 over the sum of the radii of the anion and cation. Next, we got to look at hydration enthalpy, right? Hydration enthalpy doesn't have to do with both the ions interacting. It has to do with just the sodium and just the chloride, right? It's the sodium alone interacting with water and the chloride alone interacting with water in different ways, right? So what's important is that we don't have this sort of sum on the bottom. We don't have 1 over distance term is different, because the distance for just the sodium alone is proportional to 1 over the radius of the sodium ion. But we also have the interactions with the chloride, from the chloride with the water, which is 1 over the radius of the chloride, right? So these are different terms, right? First, we have 1 over the sum of the 2 radii, because the ions are interacting with each other. And then we have 1 over each of the different radii summed together. And that's because the ions are not interacting with each other now, but they're both interacting, but with different things. They're interacting with the water, right? So that's why we have 1 over R plus 1 over R minus. The 1 over R plus tells us the sodium interaction or the cation interaction. The 1 over R minus tells us the anion interaction with the water. And we can take the ratio of these two things. And if 1, for example, we take the hydration enthalpy divided by the lattice energy. So if this ratio is greater than 1, what does that tell us, right? If this ratio is greater than 1, that means delta H of hydration is bigger than delta H of lattice energy, which means that it's probably going to be soluble, right? The energy lost by the interactions with the water are more than the energy it took to sort of break the ions apart, right? So we have a net favorable interaction, whereas the other way around, we would have a net unfavorable interaction, and probably it would be not soluble, right? So if we do this division, we end up with this formula. We have the sum of the radii squared, sum of the radii of the anion cation squared, divided by the product of the radii. And so for example, if R plus and R minus are very different, the hydration enthalpy is much more negative than the lattice energy. So if R plus, R minus different, hydration enthalpy is much more negative than lattice energy, which means that salts with a large difference in cation-anion radius are more soluble. So let me just restate that because I kind of fumbled it a little bit there. If we have R plus and R minus that are very different, this implies delta H hydration is much greater in magnitude than delta H lattice energy. Technically, delta H hydration is negative and delta H lattice energy is positive because this is a release of energy, this is a input of energy. But the magnitudes for delta H hydration will be much greater if these terms are very different. So that means that salts very different in cation-anion radius will be more soluble. And this can also be explained with a certain theory called hard soft acid base theory, which I'll talk about in future videos. But this is another interesting way to sort of see this trend is by looking at the potential energies of the products and the potential energies of the reactants, where the product is the salts dissolved in water, and the reactant is the salt together, as an ionic compound. All right, so that's basically all I wanted to talk about in this video. I hope you learned something. Thank you guys so much for watching, and I'll see you in the next one.